There's a turbocharged 4-cylinder engine sitting in a showroom right now that produces more horsepower than a V8 from 20 years ago. It weighs less, it burns less fuel, it meets emission standards that didn't exist a decade ago, and statistically, it will probably need major repairs before that old V8 would have. Not because the engineers who designed it were careless, not because the company cut corners, but because that engine is solving a completely different problem than the one you think it's solving. And once you understand what problem it's actually designed to solve, the whole story of why newer engines fail starts to make a kind of sense that's both logical and deeply uncomfortable. We've been taught to believe that progress is linear, that better engineering leads to better outcomes, that a modern engine packed with computer-controlled systems and precision manufacturing should outlast something built with carburetors and distributor caps. It feels fair, it feels rational. And for most of human history, it was true. But somewhere in the last few decades, something fundamental changed. Not in the quality of engineering, but in what engineering is being asked to achieve. Consider what's actually happening inside a modern, turbocharged direct injection engine. The turbocharger compresses incoming air, raising both pressure and temperature. Direct injection sprays fuel at extremely high pressure, sometimes exceeding 2,000 psi, directly into the combustion chamber at precisely the right millisecond. Variable valve timing adjusts the opening and closing of valves continuously, optimizing for power, efficiency, or emissions depending on load. An exhaust gas recirculation system routes a measured amount of exhaust back into the intake to lower combustion temperatures and reduce nitrogen oxide formation. A particulate filter captures soot. A catalytic converter transforms harmful gases. And overseeing all of this, a network of sensors and actuators feeding data to an engine control unit that makes thousands of decisions per second. Each of these systems exists for a reason. Each solves a specific problem. Turbocharging allows a smaller engine to produce the power customers expect while consuming less fuel under light loads. Direct injection improves efficiency and reduces carbon dioxide emissions. Variable valve timing optimizes performance across a wider range of engine speeds. Emissions controls meet regulatory requirements that are not optional. These are not frivolous additions, they are responses to real constraints. But here's what happens when you add complexity. Every system you introduce creates new interdependencies. The turbocharger needs oil flow and cooling. The direct injection system requires high-pressure pumps and precise injectors that are sensitive to fuel quality. The variable valve timing relies on oil pressure and solenoids that must function perfectly. The emission systems need sensors that can fail. And all of it must work together, coordinated by software, with no room for partial failure. In reliability engineering, there's a principle that feels almost cruel in its simplicity. The reliability of a system is not the sum of its parts, it's the product. If you have 10 components, each with a 99% reliability rate, the system as a whole has roughly a 90% chance of functioning correctly. If you have 50 components, that drops to 60%. The math is unforgiving. More parts don't just add more things that can fail, they multiply the probability of failure. An older engine, mechanically simpler, might have fewer than a dozen critical systems. A carburetor that meters fuel through vacuum and mechanical linkages. A distributor that times ignition with a rotating shaft and contact points. A cooling system with a thermostat and a belt-driven water pump. If one component fails, the others often keep working. The engine might run poorly, but it runs. A modern engine has hundreds of sensors, actuators, and control systems. A single failed sensor can trigger limp mode, cutting power and performance to protect the engine from damage. A malfunctioning purge valve in the evaporative emission system can prevent the car from starting. A crack in an intake manifold can create a vacuum leak that confuses the mass airflow sensor, leading to misfires and fault codes. These failures don't mean the engine is poorly designed. They mean the engine is tightly integrated, and integration creates fragility. So why do engineers design this way? Because they don't have a choice. Not really. Emissions regulations in most developed countries are not suggestions. They are legal requirements with financial penalties for non-comp. Fuel economy standards dictate the average efficiency of a manufacturer's entire fleet. Customers expect a 4-cylinder engine to accelerate like a 6-cylinder. They expect smooth, quiet operation. They expect instant throttle response. And they expect all of this while paying less at the pump. Engineers are not optimizing for maximum lifespan. They are optimizing within a cage of constraints. Build an engine that meets emission standards, achieve the required fuel economy, deliver competitive performance, keep manufacturing costs within budget, ensure it survives the warranty period without failure, and do all of this while competing against other manufacturers who are solving the exact same puzzle. What changes when you look at it this way is the definition of success. Success is no longer measured in decades. It's measured in regulatory compliance, market competitiveness, and warranty claims per 1,000 vehicles. An engine that lasts 15 years but fails emissions testing is not a success. An engine that is bulletproof but costs twice as much to manufacture is not a success. An engine that runs forever but gets poor fuel economy loses customers to competitors. And the business model has shifted beneath all of this. 30 years ago, many buyers expected to own a car for a decade or more. They paid cash or took short loans. Longevity mattered because they would live with the consequences. Today, the average new car buyer in many markets leases or finances over 5 to 7 years. They trade in before the warranty expires. The question is not whether the engine will last 300,000 miles. The question is whether it will last 80,000 miles without a major issue. And if the answer is yes, the design is successful. This is not planned obsolescence in the sinister sense. It's alignment with market behavior. If most customers replace their vehicles every 6 years, engineering for 30 years of service is economically irrational. It adds cost without adding value that the customer will pay for. The manufacturer that over-engineers for longevity either raises prices and loses sales, or absorbs the cost and loses profit. Either way, they lose. So you end up with a paradox that feels wrong but is perfectly logical. An older, simpler engine with fewer features and worse emissions might outlast a newer engine that is objectively superior in performance, efficiency, and regulatory compliance. Not because the newer engine is badly made, but because it's making sacrifices. It's choosing complexity to meet demands that the older engine never faced. The older engine wins the longevity contest by not entering the efficiency contest, the emissions contest, or the power per liter contest. It's optimized for a different game. And when the rules of the game change, the winners change too. Think about what this means. It means that better is not a single axis. It's a constellation of competing priorities. An engine can be better at emissions and worse at longevity, better at power delivery and worse at simplicity, better at meeting today's regulations and worse at tolerating neglect. These are not contradictions, they are trade-offs. And the uncomfortable truth is that reliability in the traditional sense is no longer the primary design goal. It's one goal among many. And when it conflicts with emissions, efficiency, cost, or performance, it often loses. Not because engineers don't care, but because the system they operate within has decided that other things matter more. There's a certain kind of engine that exists in memory more than reality now, built with iron blocks and forged internals. Over-engineered not by intention, but by the standards of its time. Simple enough that a competent mechanic could rebuild it in a weekend. Tolerant of poor fuel, irregular maintenance, and abuse. These engines weren't better at everything. They were worse at most things by modern standards. But they were robust. And robustness came from having fewer ways to fail. The engines being built today are marvels of engineering. They extract power and efficiency from physics in ways that would have seemed impossible 40 years ago. They run cleaner than anyone thought possible. They meet standards that are rewritten every year to be more demanding. And they do all of this while being lighter, smaller, and quieter than their predecessors. But they are not built for the same world. They are built for a world of lease cycles and software updates. For a world where emissions matter more than ease of repair. For a world where customers expect refinement and performance, and where longevity beyond the warranty period is someone else's problem. When a modern engine fails sooner than an older one, it's tempting to see it as a step backward, as if something was lost, as if engineers forgot how to build machines that last. But that interpretation misses what's really happening. This isn't the story about declining skill. It's a story about changing objectives. Modern engines are not built to win the same game their predecessors were playing. They are not designed for a world where durability alone defines success. They are designed for a world of strict emissions laws, aggressive fuel economy targets, competitive performance benchmarks, and price sensitivity. A world where an engine must do more with less margin for error under far tighter constraints. These engines are asked to extract more power from smaller displacements, to operate cleaner than ever before, to integrate seamlessly with software, sensors, and regulatory systems, to satisfy customers who expect refinement, responsiveness, and efficiency all at once, and to do it at a cost that keeps the vehicle competitive in a crowded market. What they are not asked to be is indestructible. In the math of modern automotive engineering, absolute longevity is no longer the dominant variable. It's one factor among many. And when longevity conflicts with emissions compliance, manufacturing cost, or market expectations, it often gives way. Not because it doesn't matter, but because other constraints matter more. This changes how we should think about failure. A modern engine reaching the end of its practical life earlier than an older one isn't necessarily evidence of poor design. It's evidence of a design optimized for a different definition of success, one measured in regulatory approval, warranty performance, fleet averages, and customer turnover, not decades of uninterrupted service. So the real question isn't whether today's engines are worse, it's whether we've quietly redefined what better means. Perhaps the engines that lasted forever were never meant to compete in today's environment, and perhaps the engines of today aren't losing at all. They're simply winning a different game, one shaped by the realities of modern technology, modern markets, and modern expectations. And once you see it that way, the story of why newer engines fail doesn't.